There we go. Everybody. You need the Simmons form. Second here. We'll get going in a couple minutes here. If I can find all the things. Only confused. Way.
Did you scan the right one? Sorry, I really left the others. I have those somewhere.
In on campus, they're probably in one of the rooms I teach in, but I couldn't find this one. I was like, oh, where did I leave them? I don't know. Let's see here. Mhm. Right. Differential equations. That's what's on deck. Just leaving, right? Sorry, see you. Yeah. Let's go ahead. It is May 7th. There was one of those things on mine. One second. We'll see about that. Okay. So what is a differential equation? It's an equation that has a function and one or more of its derivatives. You actually don't even have to have the function itself, but you have to have at least one of its derivatives. So a differential equation is an equation typically involving a function, we often call it y, and one or more of its derivatives. Some examples. Dy dt equal to 2 times y. Or dn dt equal to 2t. Or f prime of x equal to 3 times f of x plus 2x. These are all examples of differential equations where you have a function and one or more of its derivatives in all of these examples. So I would say that all of these differential equations are first order differential equations because the only derivative that's involved is the first derivative. So these are all examples of first order differential equations. We often abbreviate differential equations as diff-EQs because it's a lot of writing to write differential equations every single time. Here's an example. Say y double prime plus 5y prime equal to 6. This is a second order differential equation. Wouldn't the second example be pure time? Well, yeah, I was about to go there. So I don't think these other classifications are super important because you don't really need to know about them in order to solve differential equations. But we do talk about differential equations being either pure time or autonomous or non-autonomous. So pure time just means that the derivative only depends on time. So this second one is a pure time differential differential equation because the derivative of n with respect to t only depends on the variable t. On the other hand, this first one I wrote, dy dt equal to 2 times y, is definitely autonomous because excuse me, sorry, because the derivative only depends on the function y and does not depend on the independent variable time. This one is autonomous. Autonomous, I can spell, sure. And finally, this third one is actually neither of those. It's not pure time because the derivative doesn't depend on just the time. So when we say pure time, that would mean that, let's see, the derivative only depends on the independent variable. So for this last one to be pure time, f prime of x would have to only depend on just x. Or to be autonomous, f prime of x would have to only depend on f of x. But since f prime of x depends on both the function and the independent variable, this is neither pure time nor autonomous, and we call it non-autonomous, and that's the case. The last one is non-autonomous. You might not like the way I've written it. An equivalent way of writing this differential equation would be to write it as, do I have enough room here? Maybe. I could write this as y prime equal to 3y plus 2t. That is the same differential equation, just using y instead of f of x and t instead of x. And it's, I think it's easier to see there that, oh yeah, that is definitely not pure time. It's not autonomous, so we say it's non-autonomous. Questions so far? What else do I have to say? Yeah. Something I want to say about this first one. I want to take a quick look at this first one here for just one moment. So looking at dy dt equal to 2 times y. This is a pretty, oh, yeah. So someone asked, so autonomous is only when y is involved. I would say autonomous is when your derivative doesn't depend on t. So yeah, if the only other thing that's in there is y. Excuse me. This differential equation is one you might already be somewhat familiar with. I would point out that we can solve a differential equation like this, right? Because all we're really saying here is the derivative of y is equal to 2 times the function y. Well, we know a solution to this. I know a derivative, I should say, I know a function, you know a function too, that if we take the derivative of that function, we end up with 2 times that function. So here the solution, which we'll talk about how to solve these a little bit later, the solution is y equal to ce to the 2 times t. If we take the derivative of that, the derivative of ce to the 2 times t is, well, I've got that constant's going to hang out. And the derivative of e to the stuff is e to the stuff times the derivative of the stuff. Oh, look, that's exactly my function y times 2. So we can see that this function, some constant times e to the 2t, is a solution to this differential equation where the derivative is equal to 2 times y. Sorry, I keep getting a little something in my throat here. It's terrible. What I want to point out is this is a situation that we've encountered before. You've probably seen some of us before when people talk about exponential growth and decay. So exponential growth stems from the differential equation where we talk about the rate of growth, typically of a population, is a multiple of or proportional to. So when things are proportional to each other, we say that they're multiples of each other, the population itself. And this is what we often think about when we think about how a population grows, right? If there are more people, well, more people can make more people faster. And so the more and more people you have, the faster the population grows. So often we say that the rate of change of a population is proportional to the population size. And that's going to lead to an exponential growth model. And really the reason that I want to talk about this is because another way of talking about this, so we say that in this case, the rate of growth, dy dt, is proportional to the population size. Why? The reason I mention this is because there's another way to say this with different words that means the same thing. Alternatively, you could say the per capita growth rate, I won't give it away just yet, but I'm gonna fill in what that is a second, is constant. Well, let's look at the equation I started with. I started with dy dt, so look at the differential equation, equal to 2 times y. What could I do to both sides of this equation to get a constant on the right-hand side? If I just want that 2, I can divide both sides by y. And so what we're actually saying here is that we can say that this is dy dt, the rate of growth of the population, divided by the population size. And that's equal to 2. So the per capita growth rate is the growth rate divided by the population size. And that's important because there's a question that we were working on yesterday where we were getting a little bit confused because we thought we were talking about growth rate and they're actually talking about per capita growth rate. It's important to talk about per capita growth rate because if I said the population is growing at 500 people per year, well, that doesn't mean a whole lot. Are we in Davis? Okay, that's a lot of people. Are we in New York? That's not a lot of people. So the per capita growth rate says, oh, if we're growing at 500 people per year per 10,000 people of population, that is a more useful, meaningful piece of information. That's why we usually talk about per capita growth rate versus just growth rate if we're talking about population sizes. Oh, okay, so yeah. I want to make sure I'm hitting the highlights here. So let's look at an example. The population growing according to the following differential equation. dn dt is equal to 1.3 times n times 1 minus n over 5. So just as a reminder, what we're saying here is that n, or if you prefer n of t, is just the population at time t. And dn dt is the rate of population growth or the rate of change of that population. So we're saying the population is growing at a rate that is depending on the population size. So a couple questions before we do anything here. What's the order of my differential equation? First, second, third, show me on your fingers or write in the chat. First, second, or third? Definitely, yeah. Don't use your middle. Okay, sorry. So there's definitely a first order because we only have the first derivative. Is it pure time, autonomous, or non-autonomous? It's not pure time. It's not pure time. If it were pure time, d and dt would have to be only depending on the variable t. So when we say something's pure time, it only depends on essentially the variable that's in the bottom part of the derivative. So this one's not pure time. It actually is autonomous because the derivative only depends on the thing that's in the top part, essentially. So really, if you look at this, if you think about it this way, if it's only the thing on top, it's autonomous. The only thing on the bottom, it's pure time. If you've got both of them showing up, it's non-autonomous. So this one is definitely autonomous. Autonomous is not a word I'm great at spelling. Autonomous, sure. We can also talk about the equilibria of this differential equation. So what even is an equilibrium? Well, an equilibrium is a value of the population size where the population isn't going to change. So equilibrium or equilibria are values of n where population size won't change. What do we mean by that exactly? Population size isn't changing, well, then the rate of change should be 0. Which means the way we find equilibria is by setting the derivative in our differential equation equal to 0. So the way we're going to do this is we're going to set this 1.3 times n times 1 minus n over 500 equal to 0 and solve for n. One of the solutions is pretty straightforward. We're either going to get n equal to 0, or we're going to get 1 minus n over 500 equal to 0. Essentially setting all of the factors equal to 0. So setting this factor equal to 0, I get 1 equal to n over 500, which means n is equal to 500. The n equals 0 one certainly, I think, makes sense, right? If you have 0 people, then the rate of change of your people is going to be 0 because you don't have any people to make more people. On the other hand, the 500 here is based on what kind of differential equation we have here. So what we're saying here is when the population is 500, the rate of change becomes 0. So, oh, well, there's something I was going to look at. I forgot to look at it. That's all right. We will come back to that. The other thing we'd like to look at here is for what values of n is the population increasing or decreasing? Well, we're going to draw the sign chart. So here's what we've got. Actually, then, well, sure, we'll talk about that. So here's n on the horizontal axis. And we know that when n is 500, n is neither increasing nor decreasing because the derivative is 0. Similarly, when n is 0, same deal. The population isn't increasing or decreasing. But remind ourselves that our differential equation is 1.3 times n times 1 minus n over 500. So between 0 and 500, let's pick a value of n to plug into this differential equation and see what we get. I want to pick something easy like 1. I plug in 1.3 times 1 times 1 minus 1 over 500. Well, 1 is positive and 1 minus 1 over 500 is also positive. So in between 0 and 500, my derivative is going to be positive, meaning my n is increasing. So n is increasing. On the other hand, after 500, like if I pick something like 600, 1.3 times 600 is positive, but 600 over 500 is bigger than 1, and 1 minus something bigger than 1 is going to be negative. So you have a positive and a negative, which is going to be negative over here. So n is going to be decreasing. I want to point out, in this section, dn dt is positive. In this section, dn dt is negative. Yeah. There's more I want to say here, but I'm not quite there yet. So, yeah. You guys are always welcome to ask questions if you have questions. Sure. So let's. I was kind of holding off, but let's go ahead and draw the phase plot. So because this is not what the phase plot's going to look like the way I've drawn this over here. So if we draw the phase plot, when you draw the phase plot, you're actually graphing on your horizontal axis n and your vertical axis dn dt. Which I will point out, we often think of dn dt as g of n, where g is a function of n. We only really draw the phase plot, just as an FYI, for autonomous differential equations, right? If this differential equation depended on t, it wouldn't really lend itself to doing this. So I'm still going to plot my two equilibria, because when n is 0 and when n is 500, dn dt is equal to 0. And then, just like we said before, between 0 and 500, we saw that n was increasing, meaning dn dt is positive. So from 0 to 500, no matter what, we should have values that are above the horizontal axis. So from here to here, it's going to do something like this. I don't know exactly, excuse me, I don't know exactly how it looks, and you don't need to know exactly how it looks. You really just need to know whether it's positive or negative. So at 0, between 0 and 500 is positive, and 500 we're back at 0. And then after 500, dn dt is negative. So it's to do something like this probably. And I don't know exactly how it looks, but I don't really care. And then since we're already talking about this, yes. So what I would say here is that 500, well, here's what I like to do. If dn dt is positive, right? So dn dt is certainly positive here. That means n is increasing. N is only living on the horizontal axis. So between 0 and 500, n increases. And on the other side, after 500, so over here, dn dt is negative. My derivative, right, the values are below the horizontal axis, meaning they'll have negative values, which means n is decreasing. So we can see that 500 is what we call a stable equilibrium, because if you're a little bit away from it on either side, you get pushed back towards it. So n equal to 500 is a stable equilibrium. And if you, although it doesn't really make physical sense here to graph this function further to the left, because it doesn't make sense to think about your population being negative. If you were going to extend the graph to the left because it represented something else where negative numbers did make sense, it would be over here like that. And then we can see completely that, oh, well, over here, dn dt is negative. And so we would say that n equals 0 is an unstable equilibrium. Because if you perturb it a little bit, if you move a little bit away from 0, you get pushed further away from 0. Right? If your population is like 2 people, well, then your rate of change is positive, so they make more people, so you move further away from 0, and you get away from your unstable equilibrium. So typically, if you're trying to, well, one way of determining stability or instability of your equilibrium is to draw this phase plane like this, and to see if your graph is going from negative to positive or from positive to negative. And you'll see if you do this enough times, oh yeah, every time, if it's positive, negative, it's going to be stable. If it's negative, positive, it's going to be unstable. Someone's asking, how do we determine stability using the stability criteria? Sure, we're getting a little bit ahead of ourselves, but I suppose we can, I mean, right, we'll definitely, yeah, might as well. So here's what I would say. At this stable equilibrium, does my graph have a positive derivative or a negative derivative? Is the slope of my tangent line there positive or negative? I see you all doing this. Someone could say a word. Negative, yes, definitely negative there, where it's stable. And where it's unstable, the slope of the tangent line is positive. So that is your stability criteria if you don't want to graph it. So what we do is we say, okay, well, my function, this is where we use this notation. So I want to stress we are not taking a second derivative. We're not finding d squared and dt squared. We're not taking the derivative with respect to t. We're taking the derivative of this function with respect to n. It's not a huge deal, but I don't want you to write the second derivative because we're not really taking the second derivative. That's why I call this g of n. What we're going to do is we're going to say we're going to find g prime of n. So it might first be nice to write g of n and multiply it out because I don't want to use the product rule if I don't have to. So we multiply this out. I've got my 1.3 times, if I distribute the n, I've got n minus n squared over 500. And then my g prime of n, the 1.3 is going to hang out. And the derivative of n is 1. The derivative of n squared over 500 is 2n over 500. You don't need to use the quotient rule there. It's just 1 over 500 times n squared, and the derivative is 1 over 500 times 2n. And then we're going to check each of our equilibria. So, and we typically call the equilibria whatever your variable is, hat. So my equilibria are n hat equal to 0 and n hat equal to 500. Then we're going to check out what's going. If we plug in g prime of 0, we're going to get 1.3 times 1 minus 0. I don't really care what the numerical value is. I just care if it's positive or negative. So since this is positive, we know that n hat equal to 0 is unstable. So g prime being greater than 0, being positive, corresponds to n hat being unstable. Like we just said when we looked at the graph, right? The graph also showed this. At 0, where it's unstable, the derivative is positive. Similarly, g prime of 500 is going to be 1.3 times 1 minus 2 times 500 over 500. That's going to be negative for sure, right? That's 1 minus 2 inside. I mean, you could certainly calculate these things, right? This one is 1.3. This one is negative 1.3. But I just care that it's negative. So that this being negative tells me that this equilibrium is stable. So n hat equal to 500 is stable. So those are the two ways typically of determining whether an equilibrium is stable or unstable. You can either do it graphically with the phase plane, or you can do it analytically with this criterion. I kind of think I prefer the graphical method, but it's also fine to do it. They're both good. Like they both have their places. Sometimes drawing the graph is really hard. Sometimes drawing the graph is really, really fast. Yeah, we might as well. So since we're already here, let me have you all try this one. So I want you all to attempt to do the following problem. So 2 parts. Part 1, draw the phase plane for the differential equation dn dt equal to, yeah, I'm going to make it a little bit hard, 4 minus n times n minus 7 times n minus 1 cubed. And then use whatever method you like to determine stability. Then use either method, although since you're graphing it already, you might as well use the graphical method. Use either method, determine the stability of the 3 equilibria. Yes, there are 3 equilibria. Of the previous problem? Sorry, someone's asking how I took the derivative of the previous problem, I think. For the previous problem, I multiplied, so sorry, and I'm covering up the problem I just asked. In the previous problem, my dn dt was 1.3 times n times 1 minus n over 500. I distributed the n to each term, so I didn't have to use the product rule, and I got 1.3 times n minus n squared over 500, and then I just used the power rule to take the derivative of n being 1, the derivative of n squared over 500 being 2n over 500. That's how I did that. So again, work on this. I'll give you 2.5 minutes. You should not multiply this out. It is factored for you so that it is easy-ish to graph. What I didn't do is keep track of the time. We'll say that's been a minute. Give you another minute and a half. Right. 30 more seconds. Okay. So how do we find the 3? So if I'm drawing the faceplane, I'm always graphing the equilibria first. The equilibria are just the zeros of this equation, which are 4, 7, and 1. And yes, positive 4, positive 7, and positive 1. So 1, 4, and a 7. Each of these factors, this is typically true, but not always true. Each of these factors have odd powers, 1, 1, and 3, which means that whenever you hit one of these intercepts, you're going to cross the horizontal axis. So I'm just going to test one point. I'm going to pick I'm gonna pick something between 1 and 4 because that seems reasonable to me. I'm gonna pick 2. If I plug in 2, 4 minus 2 is positive, 2 minus 7 is negative, 2 minus 1 is positive. So I have a positive times a negative to the positive, so the whole thing is negative. So between 1 and 4, no matter what I pick, it's gonna be negative. Gonna be something like that. And then you could do the same thing for each interval. You could pick something between 4 and 7 and say like 5. 4 minus 5 is negative, 5 minus 7 is negative, 5 minus 1 is positive, and the negative is negative, and the positive is positive. Or you could just say odd power at 4 means we're going to switch from negative to positive or positive to negative. So from 4 to 7, I'm going to be above. And then after 7, well, 7 came from this factor, also to an odd power. We're going to cross the axis again, go down like that. Similarly to the left of 1, well, I should cross there because 1 came from this factor, which also has an odd power, which means we cross like that. My graph looks something like that. Again, if you want, you can test points in each interval, but if your powers of your factors are odd, you're going to cross the horizontal axis each time. If you do have an even power, unfortunately, you bounce. And that's kind of, I say unfortunately, because when you bounce, it's not really clear if you have a stable or an unstable equilibrium. It can be kind of stable on one side and unstable on the other. So that's why we don't really like that situation. As far as determining stability, so it looks, and so this is where I like to draw the little arrows. So if you're right, it's not whether this is increasing or decreasing, it's that if the graph has positive values, that means the derivative is positive, and so that means n is increasing in this interval. And if the graph is below the horizontal axis, that means n is decreasing, so it's getting pushed to the left. And then between 4 and 7, it should be increasing. Between 7 and on, it should be decreasing. So it looks like there are 2 stable equilibria. So n hat equal to 1 and n hat equal to 7 are both stable equilibria, whereas n hat equal to 4 is an unstable equilibrium. I meant to watch his video from Brandon because someone was asking about like, he talked about like a marble and being like at the bottom versus at the top. I don't feel like that's a great analogy because we're not really looking at like this part or this part. We're looking at like right here, but I don't know exactly what he said. So I need to go watch it. I meant to do that. I totally forgot to do it. So I would just say, if you look at the graph, you can kind of figure out what's going on. That's how I really would do it. So let's kind of go back a little bit because there's a few things we should talk about. Okay, kind of got ahead of ourselves, totally fine. To talk about solutions of differential equations. Not solving them yet, but verifying solutions, because I know I would ask a question like this on an exam. If I can move this paper. So here's what I mean. Verifying, not finding, just verifying solutions to differential equations. Wow, that's a Q. Sure, that's a Q. Sorry about the writing. Verifying solutions to differential equations. So let's look at the following one. We want to show or verify, whatever word you prefer, that y equal to x minus 1 over x is a solution to the differential equation x times y prime plus y equals 2x. So we're not being asked to solve this, we're being asked to show that this function is a solution to this differential equation. By the way, just as a kind of general statement, when we are solving differential equations, the solution is a function. Right? We're going to find like y is some function of x or n is some function of t, but you're going to write out the whole entire function, not just a numerical answer. So here's what we do. if we want to show that y equal to something is the solution to this differential equation, I'm going to look at what derivatives are in my differential equation. This differential equation has y prime and just y. So I know I need y prime. So I'm going to take my solution, y equal to x, and I'm actually going to write it as minus x to the negative first, so it's easier to take the derivative of. I'm going to find all the derivatives that show up in my differential equation. In this case, it's just y prime. So y prime is equal to 1, and then the derivative of minus x to the minus first is going to be plus x to the minus second, because the minus 1 comes down and makes it positive. And then what I'm going to plug these into the left side, or whichever side is appropriate of this equation. So if I take both of these and plug these in, I'm going to get x times y prime, which is 1 plus x to the negative second, plus y, which is x minus x to the negative first. And I'm not just going to say it's equal to 2x. That's what I want to happen, but I'm actually going to do the work to show that I get that it's equal to 2x. So let's see, if I multiply with the x, I'm going to get x plus x times x to the negative second is x to the negative first. And then I have a plus x minus x to the negative first. X to the negative first minus x to the negative first is 0. And x plus x is equal to 2 times x. Oh, that's what I wanted. So that's the very generic idea of showing or verifying that a given function is a solution to a given differential equation. You look at your differential equation, you find whatever derivatives you need, and then you plug them into the whole setup to make sure that you actually are getting what you want. Let's look at another example. We're going to show that y equal to sine of 3t is a solution to the differential equation y double prime. Let me double check here. Yeah, plus 9y is equal to 0. At least I hope it is. We'll find out. So here, unlike the first one where we only needed the first derivative, here we actually only need the second derivative. But to get to the second derivative, you have to go through the first derivative. So why don't actually you all do this? Find the second derivative, and then plug it in and plug in the function and see if it works. That's so if we find y prime, the derivative of sine of 3t is cosine of 3t times 3. Find the derivative of that, we're going to get negative sine of 3t times 3 times another 3, so times 9. And if we plug each of these things in, well, I should say, if we plug this in, that in, y double prime is going to be negative 9 times sine of 3t plus 9 times y is going to be sine of 3t. And if we add those together, oh yeah, they do add up to 0. So we definitely do get 0. Check. Question, yeah. Yep. So the equation says y double prime plus 9y equals 0. So if I'm trying to show that this function y is a solution, I'm finding its second derivative. So I took its first derivative, which was cosine of 3t times 3, and then I took the derivative of that to get the second derivative, which is going to be negative sine of 3t times 9. So that's what I'm plugging in. I just put the 9 in front. So that's what I'm plugging in there. And then the y, what y is equal to, that's what I'm plugging in right there for the y. I will also mention that cosine of 3t is also a solution to this differential equation. You should check that out yourself sometime. Let's look at one more like this with a little bit of a twist. So, whoops, oh, geez, okay, what am I doing here? All right, come on. So, here's another example. For what, excuse me, values of r does y equal to e to the r times t satisfy the differential equation y double prime, sure, plus 5y prime minus 24 equal to 0. I'm sorry, 24y, apologies. So we're going to start off the same way. Gosh, sorry. We're going to start off by assuming, as we're told, that this y equals e to the rt is a solution to this differential equation. So we're going to find its first derivative and its second derivative and plug those things in, assume that it's going to equal 0, and then find the values of r that actually make that true. So let's find our derivatives. So y is e to the r times t. We're pretending like r is a constant. Y prime is going to be e to the r times t times r. And y double prime is going to be e to the r times t times r times another r. So e to the r times t times r squared. And then we're going to substitute each of these things into their appropriate places. So this differential equation is going to become y double prime, which is e to the rt times r squared, plus 5 times y prime, which is 5 times e to the rt times r, minus 24y, which is 24 times e to the rt, equal to 0. Now looking at this, each of these three terms have something in common we could factor out. They all have an e to the rt. And I'm trying to solve an equation equal to 0. Typically, our method of attack is to factor out as much as you can. So I'm going to factor out e to the rt. Also, notably, e to the rt is never equal to 0. So we're not going to get a solution from that part. So we kind of ignore it almost. So e to the rt, we're left with an r squared here, a 5 times r there, and a minus 24 there. And gosh, wouldn't it be great if that factored further? Sure would. Does it factor further? Are the numbers that multiply the negative 24 and a half to 5? There sure are. The fact is r plus 8 times r minus 3. So then the values of r that make this y equal e to the rt satisfy this differential equation are specifically r equal to negative 8 and r equal to positive 3. So that means the function e to the 3t and e to the negative 8t, both those functions are solutions to this differential equation. Amelia, you had a question?
I was just saying, because e to the rt doesn't go to 0, right? So that's just like.
Right, yeah, right, exactly. You could set each thing equal to 0. You could say I'm going to set r minus 3 equal to 0, and r plus 8 equal to 0, and e to the rt equal to 0, and r equals, this one obviously gives you r equals 3, this gives you r equals negative 8, and this gives you nothing. Because e to the something is always positive. Cool. Right. Yeah. Visualizing solutions, that's not my favorite part of this, but we'll take a quick look. Sometimes it's useful to try to think about what the solution to a differential equation just looks like without actually trying to solve the thing. As you might have already gathered from the way I'm saying it, I don't love this part of it because I'm not good at it. To be really honest, like I'm just not good at it. But I'll show you a couple examples. That doesn't mean you couldn't be good at it. It just means I am not. Visualizing solutions to differential equations. So let's look at an example. Let's start with an easy example, like y prime equal to negative y. So we have to be careful because sometimes we graph different things. Sometimes, like in the previous phase planes we were graphing, the horizontal axis was your function and the vertical axis was the derivative of the function. Not what we're going to be graphing here. Here we're going to be graphing in the more typical way. We're going on the horizontal axis our independent variable t, and on the vertical axis our function y. So we're trying to think about graphing y as a function of t, based on the fact that the derivative is always equal to the negative of the y value. So for example, if y is, say, 1, then the derivative is -1. So the slope is very kind of negative there. Like that. And then, all right, am I thinking, I see, I told you I was bad at this. If we go, so if the y value, oh, I see, but then we're going to be moving downwards, right? So like if I move a little bit over to the right here, then my y value is less. If my y value is less, like 1/2, then my slope is like -1/2, which is a less steep slope. So over here, it's going to be more like that. And so I move further to the right, we move further right, my slope is negative and less steep. On the other hand, if we move further left, if I think about going this way, well, if I move up here like that, well, now my y value is higher. Sorry, you can't really see that. So my slope is going to be steeper. Like if y is, say, a value of 2, my slope is going to be -2, which is a steeper negative slope. It's going to look more like that. So maybe, and this is where I'm really bad at this, maybe my graph looks something like this. Oh, wow. Geez. See, I told you. I warned you. Sorry about that. It looks like it might be some exponential function. In fact, I'm sure it's an exponential function because I know the solution to the derivative equal to a multiple of my function is always an exponential. The solution here is probably something like y equal to c e to the negative t, where depending on your initial condition, you might have a graph that looks like this, but alternatively, this could also be a solution. Because maybe your initial condition said you start below as opposed to above. So visualizing the solution based on just your differential equation is kind of weird. There's lots of different solutions depending on where you start. And that's where you start talking about like the slope field kind of stuff, which again, I'm not very good at, to be really, really honest. Yeah, Amelia.
So when you said it moved further right, like along like the T axis,
Uh-huh.
but then like there's no T.
Right. But the thing is, from here, the direction I'm moving is in the direction that the slope of the tangent line is. So I said, okay, right here, y is positive, and I just made it up. Right, I really like just made it up. I said, if y is positive, I pick the value of 1, then my slope is going to be -1. If my slope is -1, that means from here, if I move further right, I have to move in that negative direction, which means I'm going to go further down or further up? Further down. And if I move over here to a place where I'm further down, then my y value is smaller, right? I've literally gone down lower to a lower y value. If my y value is lower, that means my value here is now a lesser number, and my slope is something more like -1/2. So then over here, if my slope is -1/2, well, then I'm starting to find out. So if I go in that way, I'm going to be even lower over here because my slope is still negative, but then it's even going to be a smaller number. So my slope is going to be like -1/4. So it's going to be even flatter. And so you just keep kind of following the trajectory that these derivatives are pointing you in. But again, you could start in a totally different place. Like I could have started down here and said, well, what my y value is? -1. Then my slope is -1, which is +1. And so then I get pushed this way. My slope over here is like that, like that. If I get pushed that way, my slope is steeper, steeper. So it's kind of funky. It's not my favorite part of this. Usually what people kind of give you sometimes is like a slope field. Have you guys seen a slope field in class where it's like a bunch of like, I can't even explain it really. It's a bunch of little like lines that point in direction. Let me see if I don't really have one on me right now. Surprised, I'm mildly surprised that hasn't been talked about in class, but not 100% surprised. Yeah, I don't have a good example on hand, unfortunately. Let me look real quick here for one thing. Yeah, there we go. One sec. Oh, where are those examples? I guess we're not, yeah, I guess we talked about that a little bit later. Sorry, we're not quite there yet. But for now, I would just say the reason you would do this is because sometimes you cannot actually solve the differential equation. And the best you can kind of do is say, well, we can look at this thing and kind of get an idea of what a solution might look like. Let's look at one more example of this, and then we will talk about things that I think are easier, to be perfectly honest, but also more fun. Let's look at another example. Let's say we want to try to visualize the graphical solution to the following. Y prime or dy dx is equal to e to the x squared plus y squared. This one is at least a little bit easier to deal with because we can pick an x and y coordinate to plug in and kind of see what things look like. So I'm going to start with what seems like an easy place for me to start, which is if x and y are both 0. So if x and y are both 0, 0 plus 0 is 0, e to the 0 is 1. The slope of the tangent line is going to be 1. So at the origin, the slope of my tangent line is going to be 1. And then anywhere else, slope of the tangent line is actually going to be steeper. Because if x and y both aren't 0, x squared plus y squared is going to be bigger than 0. So if x is not equal to 0 and y is not equal to 0, then x squared plus y squared is bigger than 0, whether they're positive or negative, and our slope is going to be steeper. And our slope, dy dx, is going to be greater than e to the 0, which is 1. So as we move, I don't know. So someone asked, do I think this will be asked on the exam? I wouldn't ask a question like this on the exam, but as you might have noticed, I am sort of biased against this because I don't like it that much. It doesn't mean it couldn't be asked, although looking at Dell's practice exam, for lack of a better word, or practice problems, I don't see any questions like this. So that's why I'm going to just do this and then we'll move on. So I'm thinking the slope is like 1 right there, and then it's going to be steeper as I move either left or right. So it's going to be kind of like that, like that. Like it gets really steep, kind of really fast. I feel like my graph isn't really even doing it justice as far as steepness here. The challenging part about this kind of idea is that there are many solution curves, right? If instead we started like at the point, say like 0, 1, then our slope starts steeper. We might look more like this. Probably similar to this, but not exactly the same. No, that's not right. So Yeah, we'll come back to this maybe after your exam because I don't think it's gonna be on your exam, but just be aware that we're eventually gonna talk about something called Euler's method, which is kind of a method for approximating what this curve looks like, which is kind of neat, actually. It's really neat when we understand what's going on with it, but I will try to, I'm gonna stop talking about this now. Move on. Okay. Oh, someone asked about that. Jeez. Yeah. So let's talk for a minute about, for more than a minute, probably, my not favorite thing also, but it's something we should talk about. The Fitzhugh Nagumo model for electrical impulse in neuron states in a neuron. And it says the following. States that in the absence of relaxation effects, the electric potential in a neuron, which we're going to call V of t, obeys the following differential equation. dV dt equal to negative V times V squared minus 1 plus A times V plus A, where A is a constant. A is a constant between 0 and 1. Is this differential equation pure time, autonomous, or non-autonomous? Yeah, are there any t's in there? Definitely not. So it definitely couldn't be pure time. And it's also going to be not non-autonomous because there are just v's in there. This is definitely autonomous. I feel like a lot of the differential equations we encounter end up being autonomous. Not all of them for sure, but a fair number of them do. So let's find the equilibria. Let's use a new page to find the equilibria. We're not gonna have enough room. So let's find the equilibria of this differential equation. And everybody should be able to identify one that's really obvious. What is it? Yeah, 0. Definitely one of the equilibria. If V is 0, this differential equation is equal to 0. So for sure, one of them is just going to be set V equal to 0. Great. But then the other one, we have to set this other part equal to 0. And that's going to be a little more work. So, or set V squared minus 1 plus A times V plus A equal to 0. Well, that's looking awfully quadratic to me. I don't see a way to factor it. I don't know how to multiply to A. Well, I think that's interesting. Could you factor this? Does this totally factor? No, that can't be right. It's totally factors. You can totally factor this. So I will point out you can factor this. Can you think of numbers that multiply to A and add up to negative 1 plus A? Well, what are the only numbers that we can think of that multiply to A? I can only think of 2 numbers that multiply to A and 1, or negative A and negative 1. And what do negative A and negative 1 add up to? Negative 1 plus A, or negative 1 minus A. So really, you can get away with factoring this. It's kind of, it's a little dicey, but you could totally factor this as V minus A times V minus 1. let's double check that. If you multiply this out, v times v is v squared, negative a times v, negative 1 times v, plus a times 1. But then we can rewrite this as v squared, and you can factor out the v, and you're left with a minus a minus 1. The minus a minus 1 is exactly negative 1 plus a. Totally works. That's super cool. So there's your other two equilibrium. Now let's say, I will fully admit, that's not super obvious, right? It's easy to not see that. I've never seen that before until I just noticed it this moment. The more typical way of solving this is to use the quadratic formula. And to say, which is unfortunate they've already used the letter A here. But if we're thinking about our quadratic formula as like, you know, f of v equal to a times v squared plus b times v plus c, using capitals just to differentiate here, then our capital A is going to be 1. Our capital B is going to be negative 1 plus a, and our c is going to be a. So then when we try and use the quadratic formula, it's going to be negative b plus or minus the square root b squared minus 4 times a times c all over 2 times a. We're going to get negative 1 plus a, so just 1 plus a, plus or minus the square root of negative 1 plus a squared minus 4 times 1 times a all over 2 times 1. And then if we simplify this, check it out, we get 1 plus a plus or minus the square root of 1 plus a squared is a squared plus 2a plus 1 minus 4a. Hey, look at that. 2a minus 4a is negative 2a. This becomes 1 plus a plus or minus the square root of a squared minus 2a plus 1 over 2. But a squared minus 2a plus 1 factors as a minus 1 squared. This really becomes 1 plus a plus or minus a minus 1 all over 2. If we add these together, the 1's cancel, and you get 2a over 2, which is a. If you subtract, the a's cancel, and you get 1 minus minus 1, which is 2 over 2, which is 1. Oh, look, the same answers. That's kind of cool. I'm not gonna lie. I'm pretty jazzed about this. This is like, it's great that you can factor that, I think. It's also totally fine not to factor it and do it this way. Yeah, cool. And there's more to say about this, but it's so terrible. Terrible, not quite terrible. It's an interesting kind of idea, but it's very, I don't know. It gets very like deep in the minutia. By the way, just to decide, I know I've said this a few times, I'm saying it again. Lots of people, a few people have asked me about specific questions on homework assignments, whatever. That's totally fine. I'll point out a lot of the ones that people are asking me about, Grant has already worked out on his webpage. So if you're struggling with a problem and looking for resources, look at Grant's webpage. A lot of like the word problems that are kind of challenging are already on there. So not that I'm not happy to talk about them, just if you're getting stuck on the homework and looking for other resources, that is a great place to look, because often the hard word problem that you're having a problem with is already in, or one very similar to it is going to be worked out already. Okay. Yeah. So that's all I have to say about that particular situation here. Let's go ahead. We talked about that already. Sure. Let's look at a few other things. Yeah. Let me ask, in class yesterday, did Dr. Dedell talk about solving differential equations yet? Okay. So let's talk about solving them, because that is, oh, wow. In the last, I thought I had a little bit more time. In the last 9 minutes here, we'll do some examples where we solve some differential equations. Sorry, the time, I guess, got away from me a little bit. So solving differential equations. And I'm guessing he only talked about solving using separation of variables so far. Or did he talk about first order linear differential equations using an integrating factor?
He started that on his own.
Okay.
So they'd be on Wednesday.
Okay, so we'll do two examples. Yeah, we can do two examples. So solving differential equations. The hope usually is that it's separable. For example, you have something like x squared plus 1 times y prime equal to x times y. Usually, if I'm trying to think about whether or not this is separable, I'm going to isolate my y prime on one side. So I'm going to rewrite this as y prime equal to x times y divided by x squared plus 1. And then the equation will be separable or is separable if you can write this side as a product of x things times as a product of x things times y things. Meaning you have to be able to separate the x things and the y things, but specifically via multiplication or division. If you have like x plus y over on the right-hand side here, you're out of luck. That thing is not separable. You have to be able to write it as a function of x multiplied by a function of y. In this case, we're happy. We can totally write this as x over x squared plus 1 times just y. And I would, instead of writing the left-hand side as y prime, I would then choose to write it as dy dx. Because what we're going to do is we're going to bring all the y things to one side and all the x things to the other side. Again, only using multiplication or division. Before you get to this place where y prime is all by itself on the left-hand side, you can do addition or subtraction if you need to get everything to one side. But once you're here, where y prime equals all the other stuff, the only two things you're allowed to do are multiplication and division to get it separated, if we're trying to separate, which we usually are. So if I have dy, whatever side dy dx is on, that side is going to be the side that ends up with y's on. The d whatever has to stay on the top. So dy has to stay on the left-hand side. So I'm going to divide both sides by y, or multiply both sides by 1 over y. So 1 over y times dy. On the right, and on the other side, I'm going to multiply both sides by dx to get dx also on top. And then we're going to anti-differentiate both sides so that we can solve for y. So we're going to say that the integral of 1 over y dy is equal to the integral of x over x squared plus 1 dx. And then we're going to anti-differentiate both sides. The antiderivative of 1 over y is the natural log of the absolute value of y. Now, for now, we're just going to ignore the absolute value. We'll talk more about it on Thursday as to why we're allowed to ignore it, but I will tell you, you can really just get away with ignoring the absolute value for the most part. So the integral of 1 over y is the natural log of y. And on the right-hand side, the integral of x over x squared plus 1, well, if we did a u sub here, we did a u equal to x squared plus 1, our du is 2x dx, our 1/2 du is equal to x dx. So we would be doing the integral of 1/2 du over u, which is just 1/2 the natural log of u. So this ends up being 1/2 the natural log of x squared plus 1. If we can double check, if we take the derivative, oh yeah, that works out. The derivative of the natural log of x squared plus 1 is 1 over x squared plus 1 times 2x. The 2's cancel. We're good to go. Plus c. Why don't we have a c on both sides? Because if we had a c on one side and c on the other side, we just subtract one of the c's to the other side and then say their difference is your new constant. So we usually put the plus c on the side that's not the function we're trying to solve for. We're trying to solve for y as a function of x. So we usually write the c on the side where y isn't. And now our job is to solve for y. So we're going to say, well, I know how to solve for, so I should say, our job is to solve for y if we can. Sometimes you'll have something like sine of y plus y squared equals some stuff, and you can't solve for y. But if this is something where we can do usual algebra things to isolate y, then we can and should. So here I'm going to write both sides as e to the stuff. So e to the natural log of y equals e to the 1/2 natural log of x squared plus 1 plus c. On the left-hand side, e to the natural log of y is just y. On the right-hand side, it would technically be fine to leave it like this, but there's also simplification we can do. Specifically, there's two things. We can first break it up as e to the 1/2 natural log of x squared plus 1 times e to the c. And then we're going to call e to the c a new constant. Some people like to call it c again. For some reason, I don't know why, I've gotten into the habit of calling it capital A. So typically, I like to call e to the c a new constant. Let's call it capital A. And then the e to the 1/2 natural log of x squared plus 1, we can write as e to the natural log of x squared plus 1 to the 1/2. Right, that 1/2 that's multiplying the natural log can come up as the power of the argument of the logarithm. But then we can rewrite this as y equal to a times e to the natural log of some stuff is just the stuff. So it's a times x squared plus 1 to the 1/2. And then if you had an initial condition, like if they said, oh, by the way, y of 0 is equal to 5, you could then plug in 0 for x and 5 for y and solve for the constant that's out in front. So if we do that here, we have 5 equal to a times 0 squared plus 1 to the 1/2. Well, 0 squared plus 1 is 1, and 1 to any power is 1. So we just get 5 equal to a. So then our actual solution is that y is equal to 5 times x squared plus 1 to 1/2. So I know that's pretty quick, but that's an example of solving a differential equation using separation of variables, where you can write y prime equal to a function of x times a function of y. The y thing comes over to the left via division. The dx comes up to the right, and then we anti-differentiate both sides. Someone asked the ln wouldn't cancel. Well, I think we did end up, I don't like to use the word cancel, I like to use the word undo here. But the natural log of y equal to the 1/2 natural log of x squared plus 1. The way we deal with that, if we're trying to solve for y, is by doing e to the natural log of that equal to e to the all that. And then we have to manipulate this. I made up the 5. So I said this is our general solution, y equal to some constant times x squared plus 1 to the 1/2. And then if they gave us an initial condition that says, oh, by the way, I know that in the beginning, at time equals 0 or at x equals 0, the amount of population is 5 birds or whatever we're talking about, then we can plug those points in, 5 for y, 0 for x, and then solve for the constant that was in our general solution. All right, Thursday, we have a test on Friday. So Thursday, we'll talk more about differential equations and also exam review. So come with questions. I did post a practice exam too. I don't know exactly how apt it is for your upcoming exam because it's just one I had right in there. But there's still some good problems on there. You should definitely look at your practice problems that he's given you. Yeah.
See if we can like study or like render this off the line and not like that.
Because it's written as y prime. So the deal here is that if we're talking about y prime, we're talking about dy dx. We're saying y is a derivative depending on x, but that also means that y is a function of x.
Would you ever have a situation where we have an x prime and like a y prime and like a differential
No.
equation?
Typically not. You only have derivatives of one function. You can have multiple derivatives. You have a y double prime and a y prime, but even then, that's really that's something that isn't done, but it's beyond the scope of what we do.
Okay.
So when we are solving differential equations, there's only two types of things we do. This, where it's separation of variables, where you eventually get your dy dx or your dn dt or your d whatever equal to some stuff, and then you pull all the top variables to the left, all the bottom variables to the right. Or the other thing we'll talk about on Thursday, which is still the same kind of idea, except you have to approach it a different way. All right. You're welcome. Yeah.
Oh, like, I guess just like, what if I made this like this solution, right? Because it's like, okay, I get it.